So today we're going to continue graphing our transformed exponential equations. And so we want to graph f of x equals 1/3 times 3 to the power of x minus 1. The first thing you want to think about is what is this parent function? And so we look at the b value, right, the base 3. And so we know our parent function is f of x equals 3 to the power of x, or maybe y equals 3 to the power of x. And so we would start our table of values with the inputs and outputs for that parent function. So again, we usually go from -3 to 3, counting by ones for the inputs for x. We substitute those into the exponent for x for the parent function, 3 to the power of x, and see what we get out. Remember, negative exponents tell you that they really belong in the denominator. That's how we're getting the 1/27th for 3 to the -3rd, 1/9 for 3 to the -2nd, 1/3 for 3 to the -1st, and so on. Now what we want to do is ask ourselves, what transformations occurred to this parent function? And as you can see, we have a 1/3 in front of our base, and we have a -1 behind the base. So we have two transformations going on. That multiplier of 1/3 is a vertical shrink because it's less than 1 but greater than 0. So that's going to impact our output. So we're 1/3 as fast as we were before. The -1 is a vertical shift down 1 unit. So again, that's going to impact our outputs, moving everything down 1. So we'll have to take 1 away from the outputs. So again, the vertical shrink, right, or stretching at 1/3 as it was before, we take all of the original outputs for f of x and multiply them by 1/3, and we can see the resulting values here in blue. Then we have our other transformation we talked about, the -1, moving it down 1 unit, shifting it down vertically. So we take away 1 from each of our previous outputs here in blue. So when we go to graph this transformed function, we are going to be using the x values and our outputs in green to make our points. Now, some of these points are easier to plot than others. If I focus on this section here of 1, 0, 2, 2, 3, 8, I can start getting the curve. I can even plot 0, -2/3 fairly easily to get that curve going. So that's what my graph in purple is, using kind of this section here for the points to form our graph. Now remember, the outputs are going to get closer and closer to -1 because we shifted it down 1 unit from that asymptote of 0. So we're going to draw the asymptote here in red, showing what it's approaching and cannot touch. We also want to be able to talk about the domain and range for this function. Now the domain is a set of all the inputs, the x values, and we can see we have no restrictions on those. That would be from -infinity to +infinity within parentheses because infinity does not stop. Our range, we're talking about the outputs, the y values, and we do have limitations there. Because of the horizontal asymptote at -1, all of our output values have to be greater than -1. So using our interval notation, that's why we have the parenthesis -1, comma, positive infinity parenthesis. So we just successfully graphed our transformed parent function of f of x equals 3 to the power of x. And again, our equation was 1/3 3 to the power of x minus 1, resulting in that purple graph. You also could have been asked about the y-intercept. Remember, you look in your table for the input of 0, and its corresponding output represents the y-intercept. So we know our y-intercept is at 0, -2/3. We do have an x-intercept where the output is 0, and our x-intercept is at 1, 0. So we could also answer that question as well if we were asked. Now that we're comfortable graphing our transforms figures, let's see if we had some table of values for functions that we've been working with recently. What patterns do you notice in the outputs, the y values? And then talk about y-intercepts. So here we'll focus on these first two. We have our function y equals 1 times 2 to the power of x, and y equals 1 times 1/2 to the power of x. So our first function, we can see 1 times 2 to the power of x. Here are the inputs, here are the outputs. And we can clearly see as we go from output to output, so every increase of 1 for x, the outputs have a common multiplier of 2. Well, how did you figure that out? You take the current and you divide it by the previous. So 8 divided by 4 is 2. 4 divided by 2 is 2. 2 divided by 1 is 2, and so on. Our second function, again, if we look at the outputs here, we've got 8 and then 4, 2, 1, 1/2, 0.25. Again, if you take the current and divided by the previous, that's 1/2. The current divided by the previous, 2/4, that's 1/2. And we can see how we get the multipliers of 1/2. So we look at the patterns of the outputs and notice that's related to the equation. Now we also want to look at y-intercepts, and y-intercepts for us, where the input is 0, we look for the corresponding output. So here we've got our y-intercept at 0, 1. Here we also have our y-intercept at 0, 1. So let's give you a moment to take a look at these two functions. And again, we're going to see in the table, what do you notice about the outputs and y-intercepts? Well, in our bottom left here, 3 times 6 to the power of x, we could see we have a common multiplier of 6. And our bottom right, we've got a multiplier of 1/4. We can see how those are carried out in the equations as well, just like we did in the two previous. Now talking about y-intercepts again, where the inputs were 0. So again, our two previous, we talked about the y-intercepts being at 0, 1. And for these, our bottom left, it's at 0, 3, and our bottom right at 0, 8. Well, we talked about how the pattern in the y column is represented in our equation. Is there a relationship about the y-intercepts? Are they represented somehow in our equation? So again, our y-intercept here was at 0, 8, and notice how we've got the 8 in our equation. Our y-intercept is at 0, 3, notice how we've got 3 in the equation. Our y-intercept on our previous ones, we're at 0, 1, and there's a 1 in the equation, a 1 in the equation. So we can see that the y-intercepts have a place in the equation as well as our rates. So here's our basic equations that we've been using for exponentials and linear. And so with our exponential equations, we've got our multiplier of a, b as our base, and x is our exponent, and then we also have our linear equations. Remember, with the exponential equations, we talked about a, that's your starting amount or your y-intercept, and b was your growth or decay factor. So growth was your multiple, so if that b value is greater than 1, and decay when the b value is greater than 0 but less than 1. So like 1/2, 1/3, think you're dividing by 2, dividing by 3. As opposed to a 2 or 3 there, multiplying by 2, multiplying by 3. So we've talked about those patterns before with our exponentials. In our linears, we've used this a lot. We know that m represents our slope, our rate of change, and that's constant, right? It's always adding or subtracting the same amount. And b is representing our starting amount or our y-intercept. So for these two equations, we can look at them and find the rates, right? The constant rate if it's linear, or the growth or decay rate, the multiplier if it's exponential. And we also can see their starting amounts, right? The y-intercept in the linear equation and also in our exponential growth to see how they are located. So what we're going to do is take a look at some table of values and some graphs and try writing the equations and determine, well, should this be a linear situation or an exponential, and fill in what we know. So if we look at this first table of values, right? X are the inputs, Y are the outputs. And we can see that the X's are increasing by 1, which is nice. And then we want to see how the Y's are changing. We go 2, 8, 32, 128. Well, we can see it's not a constant rate of change when we're adding or subtracting something. So in perhaps say multiplier situation. So you take the current divided by the previous. What do I mean? I take 128 divided by 32, see what I get. 32 divided by 8, see what I get. 8 divided by 2, see what I get. By looking at those ratios, we can see that we have a multiplier of 4 going on here. So because we have a common multiplier of 4, this is going to be an exponential growth situation because 4 is greater than 1. Now we're looking for a y-intercept. So we always look at the table and say, okay, do we have an input of 0 given to us? If so, we know the y-intercept right away. And we do. We have the input of 0 and the output is 8. So we know our y-intercept is at 0, 8. If we know the multiplier and we know the y-intercept, we should be able to write the equation. Remember that pattern, y equals a times b to the power of x. Our a value is going to be the y value of the y-intercept, that's 8. And the b value is our multiplier, which is 4. So our equation would be y equals 8 times 4 to the power of x. And again, we said that was exponential growth. Looking at this table, again, look at the inputs. There's a change of 1, so that's good. And now we want to look at the outputs to see if there's a constant rate of change. Are you adding or subtracting the same value, or is there a common multiplier? And we're going to negative 11, negative 7, negative 3, negative 1. We can see that we're increasing by 4 each time. So that's a constant rate of change. So this means it's a linear situation. We have a slope going on. So now we want to look to see, do we know our y-intercept? So again, does our table of value contain an input, an x value of 0? It sure does, at negative 7. So we could write our linear equation. We could have y equals 4x minus 7, or maybe you wrote y equals negative 7 plus 4x. That's the same equation, right? This is our linear equation. Here's another table. So again, we're checking the inputs. We can see that they are increasing by 1. So we can talk about every 1 increment, which is good for us for the inputs. Now let's take a look at the outputs. We went from 50 to 10 to 2 to 0.4. So it's decreasing. The question, is it decreasing at a constant rate, subtracting the same amount, or do we have a multiplier that's making it decrease? So again, we're going 50 to 10 to 2 to 0.4. That's not going to be a constant rate, so it can't be linear. So check your ratios. Do 0.4 divided by 2, 2 divided by 10, 10 divided by 50. We can see we've got that rate of being 1/5 as your multiplier. So our common multiplier is 1/5. If you use a decimal, that's 0.2. So we've got the multiplier. If it's 1/5, we know it's exponential decay because that's less than 1 but greater than 0. Look in the table and see, do you have a y-intercept? Is your input of 0 there? And it is. It's at 10. So if I put this all together, my equation would be y equals 10 times 1/5 to the power of x. Here's another equation. Let's see if we can write the equation table. We've got the table. Let's write the equation to represent it. So again, the inputs are going up by 1, so that's good for us. Now look at the outputs. 6, 2, 2/3, 2/9. Do we have a constant rate of change or a multiplier? In this case, we have a multiplier. Taking the current divided by the previous, we can see that our multiplier is 1/3. Do you see a y-intercept in your table? I have an input of 0, the output is 2, so my y-intercept is at 0, 2. Putting them together, our equation should be y equals 2 times 1/3 to the power of x. Again, that's exponential decay because the multiplier of 1/3, that common ratio, is less than 1 but greater than 0. Hopefully you're feeling confident writing equations, whether linear or exponential, from a table of values. Now, let's look at graphs. Graphs are just a visual representation of a table of values. You always could take points and create a table and use the same methods as what we've done before. So if we did that, these are the 3 values we can work with. Now, we can see the x's are increasing by 1 each time, and how are the y's changing? Hopefully you can see that you do have a multiplier of 3, so we have an exponential equation. We also can see we have a y-intercept visually on the graph, and we can see in the table as well, it's at 0, 4. So if I put those items together to write my equation, I would have y equals 4 times 3 to the power of x for your exponential growth. Here's another graph. By looking at the graph, we should be able to tell that this is an exponential growth just based on the shape. The table, you know it's also increasing because the outputs are going up. Now, what's the multiplier? Again, take the current divided by the previous. 18 divided by 3, 3 divided by 1/2. What do you get? You've got a multiplier of 6. We can see our y-intercept on the graph in the table is at 0, 1/2. Put them together for your equation. We have y equals 1/2 times 6 to the power of x. Here's another graph, and we should be able to tell by looking at it that it's a linear equation. So, do we see our y-intercept? We sure do. It's at 0, 1. Now, we are going to have a constant rate of change, so we have to find the slope. So we want to pick any 2 points on the line to find the change in y over the change of x, your slope. So how are they changing? The outputs are going down 2 for the inputs going up by 3. So our rate of change, the slope, is negative 2/3. Visually, you also can see you're going down 2 units into the right 3. We've talked about the y-intercept, and if we put them together, our equation would be y equals negative 2/3 x plus 1. You also could write it as 1 minus 2/3 x for your linear equation. Let's try another graph. Again, we can see it's got the shape of the exponential and it's decreasing, so it's exponential decay. We also can see our y-intercept is at 0, 10. If you'd like to arrange it in a table of values, you're welcome to do so. But again, we want to see how are the outputs decreasing. And we can see that they're going down by a multiplier. That rate is 1/5, or 0.2 if you did it as a decimal. Remember, current divided by previous, 2 over 10, 10 over 50. Put together your y-intercept and your multiplier for your equation in the exponential format, and you should have y equals 10 times 1/5 to the power of x. Again, exponential decay. If you'd like to use the decimal equivalent of 1/5, that's 0.2, that's perfectly fine as well. So today's lesson, we worked on reviewing very quickly how to graph transformed exponential equations using the transformation table. We also talked about how we could write linear and exponential equations looking at table values and graphs, looking for y-intercepts and the constant rate of change or the ratio, the multiplier for your data.